Okay, welcome to the next class on variational methods. We will continue where we left off last time, and this is the diffusion equation. I talked about diffusion processes, and to recap, the key idea in diffusion is that there are two equations that basically govern the diffusion process in physics. One equation is called Fick's law, and it states that if you have a concentration difference, so a gradient in the concentration, meaning the concentration U of your substance changes from one point to its neighbor point. That corresponds to a gradient being non-zero, and as a consequence you will observe a flow of that substance called J, and the flow is proportional to the negative gradient, and the proportionality constant is called G. And that G is the diffusivity. It basically tells you how fast a substance diffuses. And that is in many ways material dependent. There are substances, liquids where some substance diffuses very fast. There are liquids where the substance diffuses more slowly. And we'll see in a little bit that there are even materials that allow anisotropic diffusion, meaning the diffusivity is different in different spatial directions. The flow will be different, and then G will not be just a scalar but a matrix. So, and these materials are called anisotropic materials. Essentially, capillars, for example, tend to diffuse in a certain direction but not in other directions. The second equation is the continuity equation. It essentially says the overall substance has to be the same in total, and that means if you have a flow of substance somewhere and the flow changes, so more substance coming in than going out, for example, then the substance amount at that location will increase. Or if there's more flow going out than coming in, then the substance will decrease. So if you look at any given location and you have a certain flow going in and a flow going out, if the incoming and outgoing flow are not the same, then clearly substance will accumulate or will decrease in that location. And so the temporal change of the substance, of the concentration, depends on the divergence, the change, the spatial derivative of this flow. And if we now plug this equation into here, we end up with this overall equation. This is called the diffusion equation. So it basically says that the time derivative of the concentration is equal to the divergence of the diffusivity times the gradient. Again, divergence and gradient can both be represented by the nabla operator. Typically, I will write divergence instead of nabla once I'm talking about vectors. So this obviously is a vector, and so when we apply the nabla operator, it's called the divergence. Let's look at the diffusion equation in one dimension. So often when you study equations, a good thing is to start as simple as possible. This is always a good strategy in science, to basically reduce things to the simplest conceivable case and look at that one first, and then step by step generalize. The simplest case is the one-dimensional linear diffusion. So we just said G equals 1. And then we have the time derivative. If you plug G equals 1 in here, you get divergence of nabla. This is nothing but the Laplace operator. And in one dimension, it's just the second derivative. So if we just have one spatial dimension, then it's the second derivative in space applied to U. And so the diffusion just says the time derivative is proportional to the second spatial derivative. That's a very simple differential equation, and then in addition we specify an initial condition, and that is to say the concentration at any given point x at time 0. So at the start of our process, meaning at some point we basically throw salt or whatever into the soup, and that is time 0, and that tells us the initial concentration at any given point. often if you put salt in one location, in the beginning it will just be concentrated at that location, and as you will know, if you don't stir the soup, it will take quite a while for the salt to diffuse. And so any cook will know it's not a smart thing to put the salt in one location. So often if you want a more homogeneous distribution, you should initialize with a somewhat more homogeneous one. So one thing you can show is that this diffusion equation actually has an analytical solution. And this is good because it allows us to understand a little bit what the diffusion does. The analytical solution, unfortunately, is not as pretty as in the case of wave equations or of the pendulum. It looks like that. Basically, it says that the concentration at location x and time t is given by a Gaussian smooth version of the initial concentration. And the Gaussian smoothing has a width square root of 2t, meaning there is a more and more of a Gaussian blurring as time goes on. And the blur kernel grows with the square root of the time. That actually means it's a fairly slow process. And indeed, this is what you observe if you implement it, meaning if you let the diffusion run twice as long, or 4 times as long, let's say you let the diffusion process run 4 times as long, you only get twice the blurring, because the blur kernel grows with the square root. And so this is one of the nice things you can read off once you have an analytical solution. You can see how does the solution change with time, for example. And this is something that you observe. Anyone who ever implemented the diffusion, when I first implemented it in the computer, the first few iterations you see things happening and you say great, and then after more iterations nothing happens, and at some point you almost feel like, is this moving at all? Is anything happening here? And what you're facing is the square root dependency, that with every additional time step less and less is happening. So it's a somewhat slow process. Here again the Gaussian kernel, just to remind you. That this indeed solves this diffusion equation, I'm not proving. I think we'll have that in the exercises, but in principle it's not so difficult to prove that some solution fulfills the equation. What you have to do is, of course, plug it into the equation and check for yourself. You will find it actually does involve some computations to prove that this really solves the equation, but it's doable. In general, this is the diffusion process. It's characterized not just by the differential equation in more than one dimension. The linear diffusion, as I said, has the Laplace operator here, the second derivative operator in say n dimensions, 2 or 3 dimensions for images typically. And in addition to that differential equation that really is the core of the process, there are additionally boundary conditions or initial conditions. This is the initial condition that tells us what is the concentration at time 0 for all pixels in the image, if you want. And then we have the third equation here, and that says what happens at the boundary of our domain. In all numerical computations, you're working with a finite domain, omega, and so the question is, what should the diffusion process do once it hits the boundary of your image? And there are many possibilities of what you might want to do at the boundary. What we do here in general, or typically, is to say the normal derivative of u is 0. That essentially means that there is no concentration leaving the image plane. And so the overall concentration in the image is fixed. if you don't implement this boundary condition properly in your numerical implementation, you will actually see errors. What you will see is if you don't implement this boundary condition properly, the brightness may either leave the image or enter the image, and the consequence will be that you see more and more blurred images, but with time the image will get brighter, or with time the image may get darker. The average brightness will change in the image, and this is something typically you don't want. In these numerical implementations, you typically want the average brightness to be preserved. And so this is why you typically impose this condition as a boundary condition. And as you may recall, it's called a von Neumann boundary condition. So we're not saying that the concentration is zero at the boundary, but or constant as in the Dirichlet boundary condition, but we're saying its normal derivative is zero, meaning no concentration leaves or enters the image. And so what we observe is that with increasing time, the solution of this process corresponds to more and more blurred versions of the input image. Here's an example. So this is the input image. This is the initial concentration of, you could either say of brightness values or the concentration of paint in some sense on, if you want to look at the picture like that. And then with time, it diffuses, as you can see here. And indeed, you see that already at time 2, there is quite some blurring. At time 20, there's more blurring. But then if you go to 22, you will not actually see any change, or very little. And so I actually scaled, went all the way to t equals 100 so that you see any kind of difference. And you will see if you then do t equal 200, it's going to look almost the same. This is the square root dependency, that the blur kernel goes with the square root of your time. And so from time 1 to time 100, there is only 10 times the blurring, not 100 times. And so with time, you will see very little change over time. This phenomenon is not unfamiliar to you. It's a standard Gaussian blurring with increasing kernel widths, and it's pretty much what you get if you have an unfocused image. If you change the lens setting and change the focal settings manually, then you will see this kind of blurring in the image. So in some sense, what we now reproduced is the Gaussian smoothing. That's not really fantastic because we already know how to do Gaussian smoothing. So you would argue here, what's the use? Why do we study diffusion? Well, it turns out this is only the linear diffusion. And with Gaussian, diffusion, you can consider the general diffusion equation and then look at G. G is your diffusivity, and depending on how you select it, you can create a whole family of quite fascinating diffusion processes. To give you a little bit of terminology of what kinds of diffusion processes you can talk about, G equals 1 or G equals constant. Doesn't really matter whether you set G equals 1 or 2 or 3. You get the same phenomenon, just, you know, with different time, basically in different units if you want. So G equals constant is called a linear, isotropic, and homogeneous diffusion. Linear means that this expression on the right-hand side is linear as a function of u. If you take 2 times u here, the factor 2 pulls out and you get 2 times that. So this is why this is called, for constant g, it's called linear. Isotropic means you have the same process in all spatial directions. Homogeneous means it's the same diffusivity in every location in space. So in some sense, isotropy is related to rotation and invariance to rotation, and homogeneity is invariance to translation. We have the same physical process. It doesn't mean the diffusivity, it doesn't mean the concentration U is the same, but it means the physical process is identical in all locations in space. If you don't know anything about your substance, this is usually a good assumption that whatever the diffusivity is, it should be the same everywhere. Similarly, if G is space dependent, we can consider a G that changes from one location to the other. Then we talk about an inhomogeneous diffusion. A diffusion process which may be faster in some locations and slower in other locations. If G additionally depends on U, this is conceivable that we have a diffusivity that actually depends on the current local concentration or some function of that concentration at that location, then it's called a nonlinear diffusion process. And I'll show you in a second examples of nonlinear diffusion processes and how you can do very nice image denoising with them. In addition, if G is not a scalar but a matrix, then we talk about anisotropic diffusion. Of course, if it's a unit matrix, then it's still isotropic, but if the matrix is no longer a unit matrix, the consequence would be that it has a different diffusivity in different directions of space. Or in other words, the diffusion process can be fast along one axis and slow along some other spatial axis. And this is called anisotropic diffusion. And indeed, there are many physical materials that are anisotropic in the sense that they propagate some substance differently in different directions. One thing I should mention at this point, now that I've clarified the terminology, in the literature this terminology is not used consistently. But really this is the standard terminology. How do we apply this to images? One of the things we may want to do is we want to do smoothing, as we said, that preserves discontinuities, that preserves strong edges. So we want a denoising of the image, but wherever we have relevant structures, maybe relevant bright-dark transitions, we don't want them to be blurred and smooth. How can we do that? Well, we can create a nonlinear diffusion process by selecting a diffusivity, for example, a diffusivity that at strong edges is small. So the key idea is, if in some location you have a strong edge, how would you know that? Well, if your gradient of your function u that approximates this image is large, then you want small diffusivity, and so the g as a function of nabla u, say at 0 it should be constant, maybe 1, doesn't really matter as I said, and then it should decay somehow. Right? And so with stronger gradient, stronger edge information, the diffusivity, we'll make it a function of that gradient, will be smaller. How you select your decaying function, to be quite honest, doesn't matter. You will see at least qualitatively the same process. Of course, you can select it this way, this way, this way, and you will get slightly different diffusion processes, but qualitatively they all have the same property. And so this is one choice, and that was popularized by Perona and Malik in 1990. This paper is very influential in image analysis, and it's been cited many, many times because it was the first diffusion process where the diffusivity was basically adaptive. It adapted to the image information in a way, as you can see, if the gradient goes larger, this goes down. Now, you might select this diffusivity. An alternative choice, just to give you one more example, is to do e to the minus some constant gamma times gradient u. That also works, right? For gradient 0, it's 1. And once the gradient goes up, it decays exponentially. And honestly, if you take this diffusivity or that one and implement both processes, at least with the human eye, you don't really see a big difference. If you select gamma and the parameter lambda appropriately, you get essentially, at least qualitatively, the same process. This parameter, there's always some parameter. Basically, it tells you how fast this decays, right? And this is called the contrast parameter. And in this model, you can see the parameter basically says if nabla u is much larger than lambda, then we have something that is essentially 0 here, or so very small at least. And if the gradient is much smaller than lambda, then we have a strong diffusion. And so this is why it's called the contrast parameter. It tells you on what scale, what kind of edges are going to be preserved and what kind of edges are going to be diffused. When I say preserved, strictly speaking, nothing is really preserved here. You can see that because this function is always positive. So we always have some diffusion. But if the gradient gets larger and larger, that diffusion gets smaller and smaller. Similarly, in this function here, basically you have a parameter gamma, and at gamma, if nabla u is gamma, you have 1 over e here, right? So this is the value at gamma would be 1 over e, because if nabla u norm equals gamma, then we have 1 here. This is 1 over gamma. No. So if nabla u norm is 1 over gamma, then we have e to the minus 1. So there are different ways to parameterize this function, but the essence is you want to make it adaptive. As I said, the Perona-Malik model had a huge impact because, as you will see in a second, you can do something like edge detection. You can denoise the image and whatever remains are the edges. Maybe one question to the audience. The process that we see here, as you can see, it's called scale, space, and edge detection using anisotropic diffusion. Is this an anisotropic diffusion? Anyone want to take a guess? Yes. Yes. Exactly. G is a scalar, it's not a matrix. So in correct terminology, this is actually not an anisotropic diffusion. It's isotropic, but it's nonlinear. So one should have called it using nonlinear diffusion. That would have been the correct terminology. But I think this is informative. You shouldn't trust even the experts. You know, sometimes it's good to check things for yourself and to validate. And at least in our terminology, the one that is agreed upon, isotropy means the diffusion is the same in all spatial directions. And this is indeed the case here. So this is a diffusion process that is nonlinear, but is isotropic because G is a scalar, it's not a matrix. There are, in fact, anisotropic diffusion processes. Here is a book that I like a lot, Joachim Weichert, Anisotropic Diffusion in Image Processing. He wrote an entire book on this, and in fact he is considered the maybe leading expert on anisotropic diffusion. And he actually propagated the use of matrix-valued diffusion to create image diffusion processes that are stronger in some direction and less in other directions. What I show here is a numerical implementation that I took from that book of this diffusion process and of the nonlinear diffusion process. So what we assume here is that we can compute the gradient and every pixel x, and we can compute that that function g on the gradient at every location. So we have g at pixels I, j. And what we can do now is we can discretize this differential equation in order to implement it in the computer. And I will actually not talk very extensively in this class about implementations, but this is one example where I do want to go into technicalities and show you, if you want to implement this process in your machine, how to do it. So the idea is that you say du by dt, you discretize that with the forward difference, so at pixel ij t plus 1 minus u at ij time t, divided by whatever time step you took, so that is your unit time step, let's call it tau. And then you discretize the right hand side. This is, as you can see, is that expression here. Divergence is the nabla operator, is the derivatives in x and y, and then g times nabla u. So if we do that, we get the x derivative of g times the x component of nabla u plus the y derivative of g times the y derivative of u. This is, of course, for a scalar valued u here, scalar valued diffusivity. And then there, as I said, there are standard ways to do the discretization of derivatives. This discretization is not entirely standard, so I decided to show you. The challenge here is that we do two differentiations, one here and one there. And of course, if you take symmetric differences with respect to your central pixel that you're looking at, the first derivative, symmetric differences, would mean you go one step to the right, one step to the left. And then if you apply yet another derivative to that outcome, then you would take one step to the right, one step to the left, meaning you would end up with a mask size of 5. Because from your central pixel, you'd have to go 2 steps to the right and 2 steps to the left. And what is clever about this discretization, as you can see, is we take a half step to the right and a half step to the left in the first discretization. So to draw that, if this is your pixel grid, and we have the central pixel here, we don't go all the way to the right and all the way to the left, but we basically evaluate in between 2 pixels, I plus 1/2, I minus 1/2, and j. And then once we discretize this, once we then apply we discretize this derivative, so we have to evaluate the x derivative at the pixel I plus 1/2 here. We go yet another half step to the right and a half step to the left, and the consequence is we remain in a 3×3 window around our pixel. And so we end up with here the discretization of the x derivative at plus 1/2 is plus 1, another half to the right, minus the central pixel, a half to the left again. And similarly for this one here. And so you end up with an expression that is defined on the central pixel uij and its 2 neighbors uij plus 1 and ui minus 1j. And quite similarly, exactly the same for the y derivative. You also go 1/2 step up, half step down, and then in the second derivative evaluation you go another half step up, half step down. And you end up with this expression that has values of u at the neighboring pixels, the right one, the left one, the center one, and similarly the upper one and the lower one. And then the question is, what do you do with the diffusivity in between 2 pixels? So this is the diffusivity between the central pixel and the pixel to the right. So we go half a step to the right, and we want to evaluate the diffusivity. One thing you could do is take the average of the 2 diffusivities. So basically you take the sum of to compute the diffusivity, say at this location, you take the sum of diffusivities at these 2 locations and divide by 2. You can do that. But what Weicker does is different. He takes the product of the diffusivities and their square root. So there's this is called the geometric mean, and this would be called the sum, and divide by 2 is called the arithmetic mean. Qualitatively, the 2 are the same. It doesn't matter, but it turns out there is a difference, and the difference is in the context of nonlinear diffusion, and this is vital. If imagine the diffusivity is 0 at one of the 2 pixels, then the product is also 0, whereas the average is not 0. So if you have a diffusivity of 0 here and 1 here, then the arithmetic mean would say you have a diffusivity of 1/2 in between. Whereas this geometric mean says it's 0. So this term is 0 as soon as one of the 2 diffusivities is 0. And the advantage of that is that if you want to preserve structures and you have some small diffusivity in some location, this discretization has a tendency of really preserving it, because G will become 0 if it's 0 at one of the 2 places. And so what you do now is you have the discretization of this term here, and a similar discretization for the y derivative, basically the same, except in I you do it in j. And then on the left hand side you have uij t plus 1 minus uij t over tau, and you can basically multiply the tau over to the right hand side and take that onto the right hand side and solve for uij t at time t plus 1. And everything on the right hand side is evaluated at time t. This is called an Euler discretization. It's the pretty much simplest discretization that you can do for these time dependent processes. And it allows you to immediately read off what is the concentration U at pixel ij at the next time step, depending on the concentration of U at time t, at the last time step. And then you can solve that for this one and just iterate in time. And it turns out you can parallelize this process very nicely. A lot of these differential equations are easily parallelized, which means you can compute the update for pixel ij at time t plus 1 simultaneously for all pixels, because it depends on the old values of these pixels and those you have. And so it's actually fairly straightforward to parallelize it, and so to update all pixels in one sweep, in one step essentially. And so as a consequence, these kinds of diffusion processes are easily run at frame rate on images nowadays. It looks a little tedious, but I mean seriously, you're simply, you know, taking differences and taking products, and so this is not a lot of computation. And so they easily run at 30 frames a second for standard size images. If you have very large images, then you may not be able to do real-time processing. Here's what you get if you implement this with this kind of decaying diffusivity. I believe it may have been the Perona Malik one or this exponential one. Doesn't really matter, as I said, but what you get is these diffusion processes. Strictly speaking, whether you take the exponentially decaying or the 1 over gradient one that Perona and Malik used, is not exactly the same. But I would bet even an expert in diffusion would not be able to tell me which of the two this one is. And so one of the things you see if you look at that diffusion process, it is very different from the linear diffusion, in the sense that over time things get blurred out, but strong edges will remain. So if you look at the chin area, for example, in the original image and in this denoised version, you have a very sharp edge here. So it's very different from a linear diffusion process in that you preserve these sharp edges. As I said, this is a nonlinear diffusion process, but it's isotropic, so it's the same in all directions, in all spatial directions, but there are more sophisticated diffusion, anisotropic diffusion processes where you can construct a a matrix valued diffusivity in such a way that it creates a diffusion and smoothing process along the edge direction, but not orthogonal to the edge direction. And in fact, this is what's usually done with anisotropic diffusion, that you smooth in the direction of the edge and you don't smooth orthogonal to the edge. And so you have a directional dependent smoothing, and your coordinate system is basically selected locally based on your gradient information. So you determine the edge directions locally in a certain neighborhood, and then that defines a coordinate system, and then you do smoothing along the edge but not across the edge. This can be done, and it improves denoising in many cases even better. I don't have examples in my slides, but you can easily find lots of examples on the web. Which diffusion process is the best suited for your particular purpose, for your particular denoising problem, is a separate matter that there is not one diffusion that works for everyone. It really depends on the applications. I've even seen papers where people argue for a diffusion process that doesn't diffuse along the edge, but it diffuses across the edge and not along the edge. To make use of that is a little bit more tricky, but there are approaches that promote this kind of diffusion process. But the nice thing is, in general, you can construct all sorts of denoising processes according to your preferences. Some that denoise along edges or across edges, or whichever. Maybe to go one step back, another adaptive diffusion process here in the Perona Malik, you can see that G scales or depends on the gradient of U. Of course, you could also use the gradient of the input image, right? You could have a diffusivity which is strong if there is no gradients in the, or little gradients in the input image, and small if in the input image. So you would have not nabla U here, but if the input is F, you would have nabla F here. This is a very different process from a mathematical point of view, because if you have a G that depends on the input image but not on U, it's still a linear diffusion process. Because the nonlinearity is with respect to U, of course. If G doesn't depend on U, but only on I, or F, whatever your input image is, then it's a linear diffusion process, but an inhomogeneous one. So your G would be space dependent. It would be different in different locations of space, but it would be the same. It would be linear. Yeah, so these are different diffusion processes. This gives you a little bit of an idea of what you can do with nonlinear diffusion and how you can do denoising in an edge-preserving way, in the way that edges are preserved. I am not sure how many times the Perona Malik approach was cited, but definitely tons of times, thousands of citations. Is one of the most influential papers in image analysis, and it sparked a lot of research in the field of diffusion filtering. And although diffusion was around before, and the knowledge that Gaussian smoothing can be represented as a solution of a diffusion process, this was known. But the whole popularity of diffusion filtering basically was initiated with the Perona Malik paper. And there are many influential papers. The most influential one is the Perona Malik one, 1990. And then another very influential one we'll talk about later in class is the Rudin Osher Fatemi. We already saw it, but this is 1992, mind you, so this is 2 years later. This so-called ROF model, sometimes is called ROF, is also, we'll see, a nonlinear diffusion process of that is qualitatively similar to the Perona Malik but slightly different in the formulation and has a lot of different mathematical consequences. Yes? So this is a good question, whether to apply this for edge detection, whether this isn't very costly. As I said, this process can be run on images 30 times a second. And so you can get this kind of denoising at 30 times a second, and then what you can do is you can apply the standard gradient-based edge detectors not to the input image, but to the diffused image. Because here the prominent gradients are there and the rest is pretty smooth. So in some sense, the idea is if you have a somewhat noisy image and you want to recover the edge, not to compute the derivative of the input, but to denoise it in an adaptive way and then compute the derivative on that adaptively denoised image. Of course, we saw even with standard derivative filters, you would first do Gaussian smoothing a little bit and then apply the filter. But here the idea is, rather than doing Gaussian smoothing before computing the derivative, do a smarter diffusion that preserves the edges. That way you get the prominent edges and they will not be dislocated as in the case of Gaussian smoothing. Because when you do Gaussian smoothing, it actually moves the edges and destroys the edges. Here, they're still there. Okay, we'll stop here. Thank you very much.